Welcome back everyone. In this lecture we will discuss about matchings, perfect matchings and Hall's theorem. So, due to time constraint I am not going to give proof of Hall's marriage theorem and all, but I will state and explain what it means. Okay, so let us start with the definition of matchings. So, we start with the graph G and then look at its set of edges. So, a matching is nothing but a subset of this given edge set E. So, let us call it M to be a matching. So, it is a matching if it is a subset of edges such that it has no loops. Okay. So, loops are not allowed, they are not part of M, and any two given distinct edges in M, they are non-adjacent. Okay. So, they should not be adjacent, that means they should not be incident in a vertex. So, such subset you call it as matching. So, for example, if we take a graph something like this, so then we can simply take this particular edge and then this particular edge. So, that is a matching. Okay. So, you do not need to actually include all possible vertices or anything. So, matching broadly speaking it is just a subset of edges satisfying that it contain no loops are allowed and any two edges are just non-adjacent. So, it is important to actually understand given when actually given a graph contains a matching that indeed saturates some given subset of that graph G. So, what I mean by that, so we say that a matching of G that saturates subset of let us say x of vertices V. Okay. So, if all the vertices of x actually they become vertices of some edge from that matching. Okay. So, then in that case we call it that matching actually saturates this subset x. So, and one is interested in knowing like so when given subset capital X of the vertices can be actually saturated by a matching. Okay. Whether we can find a matching that saturates every vertex in that given capital X. So, this type of problems actually naturally motivated from some practical problems that we find in real life. Okay. I do not have time to explain all those things. So, maybe you can again Google it and then find some nice applications. So, let me just state an important theorem about such matching finding. So, which is proved by Hall. So, it is called Hall's theorem or Hall's marriage theorem, because it has some nice applications in some marriage problem. So, which actually talks about when a bipartite graph that can have a matching that saturates some particular subset of vertices. So, here is the theorem. So, let me state the theorem. So, let G be a bipartite graph. So, with the bipartition, bipartition let us say x and y. Okay. So, we have the set of vertices x on one side, the set of vertices y on other side. So, edges actually go between x and y. So, then we want to actually ask whether G contains a matching that saturates every vertex in x. Okay. And we can actually tell when it happens. Okay. So, then G contains a matching that saturates every vertex or vertex of x or vertex in x if and only if. So, what happens? So, you look at any subset S of x, okay, and then look at its neighborhood of S. So, the cardinality of the neighborhood must be greater than or equal to the cardinality of S. Okay. The number of vertices in S should be at least the number of vertices in the neighborhood. So, what is neighborhood? Okay, the neighborhood or the neighbor set of S in G, it is the collection of vertices that are adjacent to the vertices in S. Okay. So, where n of S is nothing but you look at all possible vertices inside V such that so there exists an edge, okay, that actually contains U and V, okay, for some V in S. Okay. So, you collect all possible vertices that actually adjacent with two vertices in S. Okay. So, then that is what you call as neighbor of S. So, then you are actually demanding that a G contains a matching if and only if saturating every vertex of x if and only if any subset S of x must satisfy this property that the cardinality of S is at least the cardinality of the neighbor of S. So, it is such a nice criterion. It is not very deep theorem, but again it is a very nice theorem to prove. Okay. As an immediate corollary, one can actually solve this marriage problem. Okay. So, let us actually state this marriage problem. It is some fancy way of stating some problem, that is all, but again like this can be stated in some other terminology as well. So, let us say we have this following problem that happening in the village. So, if every girl in a village knows exactly k boys, okay, and every boy knows exactly k girls. So, then can we actually assign can we pair girl and boy such that each girl can marry a boy that she knows and each boy can marry a girl that he knows. Okay. So, you have these boys here and then you have these girls here. So, let us say each boy actually knows exactly k girls. Okay. So, that means, so you have like the degree of this boy is exactly being k. So, by knowing you can actually put an edge between girls. Okay. Similarly, each girl knows exactly k boys. Okay. Again the degree of this is k. So, basically what we can do, we can produce what is called a k regular bipartite graph. So, what is k regular means, if all the degrees are same which is exactly k, then you call it as k regular graph. So, now k regular bipartite graph is easy to make. You can put the boys in one set and then girls in the another set, and then you can put between boys and girl edge if they know each other, and that way the statement hypothesis can be translated into defining this k regular bipartite graph. Now, given this condition, then we are asking whether can we get assignment so that each girl can marry a boy that she knows and each boy can marry a girl that he knows. So, that means we want to actually find a matching. So, we want to find a matching in this graph such that all the vertices in B should be saturated. But since it is a k regular bipartite graph, that would imply that the number of boys and number of girls also should be equal. So, that would tell you that whatever we are getting is indeed a perfect matching. So, that means each girl can marry a boy that she knows, and each boy can marry a girl that he knows. So, indeed what we are looking for is actually perfect matching in this graph. And indeed it is a easy consequence of Hall's marriage theorem that given any k regular bipartite graph with k being at least 1, we can have a perfect matching. So, perfect matching means in this scenario we have used all the vertices. Okay. So, let me state it as a theorem, and it is not hard to prove as a corollary of the Hall's marriage theorem. If G is a k regular bipartite graph with k being greater than or equal to 1, so then G has a perfect match. Okay. So, let me just quickly outline, it is not very hard problem. So, let us say we have given this bipartition of G. So, then we have x here and then we have y here. Note that the degree of any vertex is k for all v in G. So, v in v of G. Okay. So, that would imply that if we take any for example, like if we take the number of edges inside our graph G, it is not very hard to see this is going to be exactly equal to k times the cardinality of x. Okay, because for each vertex we are going to have k number of vertices adjacent to that vertex. So, now if you list all of them as some VR, so each one will have k. So, then k times r is going to be the number of edges. Similarly, the same argument holds for on the right side as well. So, the k times the cardinality of y is exactly the cardinality of the edge set. So, that implies immediately the cardinality of x must be equal to the cardinality of y. So, now what we are going to do? We are going to look for this matching that saturates x. If we find a matching that saturates x, since cardinality of x equal to cardinality of y, that becomes perfect matching. So, for that we need to verify the condition in the Hall's theorem. That means the neighborhood of any s should have at least the cardinality of s number of vertices for all s subset of x. So, this is the condition that we need to verify. So, let us fix s inside x. So, then look at the number of edges incident with vertices in S and vertices in N of S. Let us call it E1 and E2. So, E1 is the sets of edges incident with vertices of S, and E2 similarly exactly, but incident with vertices of N of S. Okay. So, then it is not very hard to see E1 has exactly cardinality equal to k times the cardinality of S, because it is a k regular graph, and E2 has cardinality exactly equal to k times the cardinality of N of S. So, now note that the by definition of N of S, so N of S is actually having, so you have S is here and then you have N of S here. So, all these things are in adjacent to this. So, by definition of N of S, what we have is E1 should be contained in E2, okay, that is obvious. So, that means the cardinality of this E2, which is exactly k times the cardinality of n of s, should be greater than or equal to k times the cardinality of s, which is the cardinality of E1. Now, by cancelling k, we get exactly the this condition star, which is cardinality of n of s is greater than or equal to cardinality of s. So, since the condition in the Hall's theorem is satisfied, so that will actually tell us immediately that G has a matching M saturating every vertex in X, but since cardinality of X is same as cardinality of Y, that matching must be perfect matching. It should include all the vertices. Okay. So, this actually it tells you that marriage problem that we stated before, that has actually solution. Okay. So, this actually with this condition we can always have a perfect matching. So, that is why called it's perfect matching, because each boy can marry each girl, vice versa. Okay. So, that actually completes the discussion about matching and perfect matchings and marriage theorem. So, now what we will do, we will actually quickly talk about some graph polynomials that appear everywhere. So, since I am very much interested in vertex colorings, so I would actually assume that given graph is simple graph, because vertex coloring do not see multiple edges between the vertices. So, it only sees whether given two vertices are adjacent or not. So, for that purpose, let us assume G a simple finite graph, okay, because we want to count things. So, that means the number of vertices is given to be, let us say, some n, and then the number of edges can be at most n choose 2. Okay. So, it is a finite graph. So, all the vertices and edges are finite. So, now what one can define? One can define actually various important quantities related to G. So, let us first start with some polynomial called independence polynomial. So, there is no standard notation, I use what is called I of G. So, I of G is denoted by summation, let us say some a k q power k greater than or equal to 0, where this a k counts the number of k independent or stable sets of G. So, let us define what is this stable or independent sets. Okay. So, you take a subset of V, okay, is called independent if when you look at the subgraph spanned by S, okay, you look at subgraph spanned by S, so that has no edges in it, no edges in it. Okay. So, that is what you call it as independent or stable. Okay. So, now you can count number of k independent sets, that means independent sets that having exactly cardinality k, and it will be finite number. So, then you can actually create this polynomial which is just counts all possible independent sets, keep tracks of that for given k how many independent sets are there or not. So, similarly, one can define what is called clique polynomial. So, clique polynomial of G similarly defined. So, you call it something as k clique. So, k clique is a subgraph of G, let us say spanned by again spanned by a subset, let us say S of V, such that that subgraph spanned by that S is isomorphic to the complete graph of size k. Okay. So, complete graph of size k. So, these are two extremes. So, this is actually has no edge and it has these clicks have all edges. Okay. So, even though they look like two different concept, one can define what is called this line graph of G, and then if you take independent subsets of the line graph, that will be exactly corresponding to the clicks of the original graph. So, now what one can do? One can define this click polynomial, which is exactly given by summation b k q power k, k greater than or equal to 0, where b k counts the number of k clicks in G. Okay. So, now let us define what is called this chromatic polynomial. So, all these polynomials, why are we defining? So, one can actually study later some algebraic properties of this polynomial, which actually tells us something more about the coefficients. For example, one can study the roots of these polynomials. They are basically polynomials defined over reals. So, now we can talk about the roots of these polynomials and then ask whether all of them have real roots or not, and so on. So, for example, if given polynomial over reals, okay, if they have real roots, so then one can immediately conclude that the coefficients they must satisfy this log concavity property. And log concavity property will tell you immediately the coefficients for example, satisfies this unimodality. So, that means they increase first and then after that it will decrease. So, it will go like this and then come like this. The coefficients plotted on the R2 will look like something like this. So, such more combinatorial properties or the behaviors of the coefficient and so on, they can be derived using these properties of the roots and so on. So, these are all the like important things that are studied in algebraic graph theory, and one also interested in where the roots are located. So, those kind of problems are also studied. Okay, anyway, they are very interesting combinatorial objects. So, it is good to count them and then study the properties of them. Okay, here is another important notion called vertex coloring. So, again so this is motivated from what is called 4 color conjunction of a theorem. So, 4 color theorem is something related to planar graphs. So, I do not have too much time in explaining all those things. So, I will just stick with the definition of vertex coloring, and then I will at least tell you that how to write chromatic polynomial using Mobius inversion. Okay, what is vertex coloring? So, you start with G being a simple graph. So, like I said, we do not care about edge colorings and all. Edge colorings also can be defined, and then we can talk about polynomials counting edge colorings and so on. But due to time constraint, let us only stick with vertex coloring. So, we have this simple graph. So, then what we want to do? We want to assign colors to the vertices. So, let us do one example. So, let us take path 3, and then what we want to do? We want to assign colors to the vertices such a way that adjacent vertices must receive different colors. For example, if I put red here, then I am allowed to put different color like blue here on the vertex 2, and then this red can reappear here because 1 and 3 are not adjacent. Okay. So, what is vertex coloring? So, vertex coloring and assignment, okay, you choose, let us say Q vertex coloring, okay, choose colors from given Q colors such that, okay, choose colors from q colors and assign them to vertices of G such that adjacent, this is the only important condition, adjacent vertices receive distinct colors. Okay. So, let us write it more mathematical term. Okay. So, assignment one can record it as a function because each vertex gets some color. So, the color that is assigned to the vertex one can treat it like a function from the vertex set to the colors. So, let us say we have q colors. So, let us label them as 1 to q. So, I am just using so I am not using like colors like C1 etc. CQ, I am just identifying with the colors 1 to q, okay, just labeling them, that is all. So, it could be like C1 etc. CQ, if you are not comfortable you can write that way, but otherwise just write it like 1 to q. So, these are all the given colors and q is just greater than or equal to 1. Okay. So, now what is coloring? Coloring is an assignment, that means it is a function from the vertex set to these q colors such that, so you have I and then you are assigning this color I, you are calling it f of I. Okay. So, the condition is that f of I should be, maybe let me use u for u and v for vertices. So, v goes to f of v, okay. F of u is different from f of v if there is an edge between u and v between these vertices u and v. So, if this condition is satisfied, this is what you call it as q coloring. Okay. So, now what we can do, like this is also like coloring at most q colors used. Okay. So, we say that two colorings are distinct, f1 and f2 are distinct, that means at least at some vertex f1 of u and f1 of f2 of u must be different. Okay. There exists u in v such that f1 of u is different from f2 of u. So, now what we can do, we can actually define a function, let us call it chi g of q, which counts the number of distinct colorings of G. Okay. It is a function of q because I am looking at all possible colorings, okay, which are functions from v to 1 to q such that it satisfies this condition f of u is different from f of v whenever there is an edge between u and v, and then we count all possible distinct colorings, then that is going to be a function in q. And note that this is a finite number, okay, this chi g of q, that is because the number of functions from v to bracket q, they are finite. Okay. So, this is indeed a function. So, what is interesting, actually it is a theorem that was proved in the beginning of 19th century. So, this is not just merely a function in q, it is indeed a polynomial function in q. So, it is indeed a polynomial in q. So, let us do some examples, so then it will be clear like what we are talking about. So, let us say we have only 2 vertices and 1 edge. So, now I want to color this graph using q colors. So, the condition that we are implementing is that the colors that are assigned to 1 and 2, they should be distinct, okay, because there is only one edge between 1 and 2. If I assign color some color to 1, some color to 2, then they should be distinct. So, now we use first order counting principle directly and then calculate this polynomial like as follows. So, for example, if I want to assign to the first vertex some color that comes from 1 to q, what I can do, I can choose any colors from that 1 to q, okay. Then I have q choice, okay. q choices are there for vertex 1, because there is no restriction for the vertex 1. So, let us say I have chosen a color, okay, for this vertex 1. So, then the only condition that I have for vertex 2, whatever color that I used for the vertex 1 should not be used for the vertex 2. So, then I have to choose some other color C2 which is different from C1. So, that is the only condition. Okay. So, that means what I can do, I can remove that particular color from the given collection 1 to q. So, then I can choose anything from that q minus 1 choices for the vertex 2. So, that means, so this is already mutually exclusive. So, that means I have q into q minus 1 number of ways to color this graph 1 2 or P 2. Okay. So, that means the chromatic polynomial of this P 2 or K 2 of q is exactly q into q minus 1. So, similar argument one can give for other graphs as well. For example, if I take something like this, which is of path P 3, okay. So, then you can easily see that we can choose any q colors for the first vertex, and then we can choose any colors for the second vertex, which is different from the color that is used for the first vertex, and we can choose any color for the third vertex that is different from whatever color that is used for the second vertex. So, that means we have q minus 1 choice for the third vertex. Okay. Let us say I have used red here, then I am not supposed to use red here, and then let us say I used blue here, then I am not supposed to use blue here. Okay. That is the only condition. So, that way you can see that the polynomial q into q minus 1 into q minus 1 is going to be the polynomial for this chi P 3 of q, which is exactly q into q minus 1 square. So, like this one will be able to compute polynomials for the small values of small graphs. So, indeed one can actually write down a very explicit formula for a big class of polynomial called Gödel graphs. Okay. So, maybe if you are more interested in these things, you can actually look it up much in the literature. So, now what I want to do, I want to actually use Mobius inversion and then demonstrate why this chromatic polynomial is indeed a polynomial. So, this chi g of q is a polynomial in q. Okay. So, that is a theorem, and this polynomial is called, it is called a chromatic polynomial of G. Okay. Okay. So, let us prove this. So, we want to actually look at all possible colors satisfying the property that adjacent vertices receive distinct colors. So, given H in E, what one can do? One can define this AE, which is you collect all possible colorings F from V to 1 to Q such that F of U equal to F of V. So, they are the bad functions, bad colorings, okay, because that particular edge both vertices they receive same color. Okay. Indeed, what we want to do, we want to remove all of them. Okay. So, the chi g of q, if you think about it, it is going to count all possible things that are in the complement of this AE for all H E in E. Okay. So, if you take the complement of AE, then we can see that it is a functions from V to bracket q such that f of u not equal to f of v, where E is that edge u v. So, now if you take the intersection of all AE complement E in E, then the condition that we have for the chromatic polynomial chromatic that function chi g of q is actually satisfied. So, this quantity indeed counts chi g of q. Okay. It counts all functions from V2 bracket q such that f of u not equal to f of e for all edges u v in E. Okay. So, now what we can do, we can use Mobius inversion, which is inclusion exclusion principle, and then we can rewrite this as follows. So, this chi g of q can be rewritten as summation minus 1 power the cardinality of S intersection of AE E in S, okay, where S comes from subset of E. But it is easy exercise to do that. The intersection of AE E in S is the cardinality is exactly q power omega of S, where omega of S is nothing but the number of connected components of this graph which has vertex at V and edge set as S. Okay. So, maybe I will use some other notation if you want. So, this S is overused. So, maybe I will call it as A here. Okay. This is A. So, why this is true? If you think about it, intersection of AE E in A. So, if you take any connected component of this VA, so VA is nothing but the graph of so whose vertex set is V and the edges are actually kind of comes from only capital A. So, then it will have connected components and then since we are looking at the intersection of AE. So, if you look at any particular connected component, all of them are actually connected by a path. So, all of them will receive same color, because f of u equal to f of v whenever that edge u v is in that connected component. So, then that means each connected component receives same color. So, that means this counting is actually same as you can choose any q colors and then assign to these connected components independently, and then you can actually get the functions. So, you assign some color 1 here and then color some r here, where r is the number of connected components. So, and then this C1 etc. C are just to chosen from 1 to q without any restriction. So, that means the number of such functions that satisfies or it is in this intersection of A in A is going to be exactly q power omega of A, that number of connected components, because each connected component is determined by one particular color and that color has no constraint and we can choose anything from 1 to q. So, there are q choices for that. So, each component has q choice. So, then q power the number of connected components is going to give us the cardinality of intersection of A. So, that means this particular chromatic polynomial can be rewritten as summation minus 1 power cardinality of S q power omega of A, where A runs over all the subsets of E. Okay. So, now we have very explicit description of this chi g of q in terms of this q powers. So, this also proves that this chi g of q is indeed a polynomial in Q. Okay. This is one nice applications in combinatorics about this chromatic polynomial of this Mobius inversion. Okay. So, this is something like one can use many methods to prove this statement. I just wanted to prove it using this Mobius inversion. So, this tells immediately that it is a polynomial in Q, but from the definition it is not very clear why it should be a polynomial in Q, but now it is very clear that it is a polynomial in Q. Okay. So, I will actually stop here. So, with this I would like to end the graph theory portion. Okay. Like I said, we wanted to actually cover few topics in graph theory in order to introduce graph theory to you, Okay, so we won't be able to do all the theorem, interesting theorem that you see in one full-fledged course in graph theory, but whatever we could do, we were able to do. So, due to time constraint, I will end the graph theory portion here. And if you are more interested in graph theory, you should definitely do proper course in graph theory. So, maybe I will think about it and then if possible I will offer a course. So, after this one actually starts with number theory, basic number theory, and then with the goal that introducing some abstract algebra concepts like rings and groups and so on using that number theory objects. Okay, so that part will be done by Professor Magesh Kakde, who is my colleague in Indian Institute of Science Mathematics Department, and he is so he will be continuing this course with the number theory part. Okay, so I hope you must have enjoyed my lectures. So I will stop here with this. Thank you very much.